Hello, welcome back. I am very pleased to introduce to you here John Posada. He's senior researcher from Utrecht University in the Netherlands. He's an expert in design of sustainable biorefineries and will present this unit.
Thank you, Patricia. Welcome to this lecture on environmental assessment of a process design. In the last weeks, you have learned how to perform a conceptual process design and an economic evaluation using the fermentative production of 1,3-propanediol PDO as the case study. In this lecture, I will present the most relevant concepts and the necessary steps to perform a systematic environmental assessment of a process design. There are several methodologies available for environmental impact assessment of a process design. This lecture focuses on the life cycle assessment methodology, LCA, since it is a widely accepted tool that allows compilation and evaluation of potential environmental impacts of a product, process, or service through its entire life cycle. In addition, LCA is standardized in the ISO 14040 series by the International Organization of Standardization. According to ISO, the LCA framework consists of 4 steps: goal and scope definition, inventory analysis, impact assessment, and interpretation. Interpretation is done for each one of the previous steps and also at the end of the analysis. LCA is a tool that is applied for decision-making support, communication purposes, and for process or product chain optimization whenever environmental considerations are taken into account. Now I will walk you through these 4 steps using the bio-based PDO production process as an example. In step 1, goal and scope definition, the purpose of the study and the problem formulation are specified. In this case study, we want to know what the environmental impacts of the bio-based PDO production processes are, and additionally, how do these environmental impacts compare to the petrochemical counterpart and also to other LCA studies. Next, the system boundaries are defined. Here, all relevant life cycle stages shall be included as far as possible. For example, a cradle-to-grave system for bio-based products covers the extraction and production of all raw materials and energy carriers used in the agricultural phase as well as in the transformation, use, and waste management phases. The last 2 phases are the same for the bio-based and for the petrochemical PDO, since the product is chemically identical and therefore the system boundaries for this lecture can be set as cradle-to-gate. Bio-based PDO is produced via fermentation of sugars, which in turn can be obtained from various sugar and starchy crops or from lignocellulosic materials, also known as second-generation feedstocks. For this lecture, the raw material selected is sugar from Brazilian sugar cane industry. The functional unit is the basic unit to perform the study and for any comparison. In this case, the functional unit is 1 kilogram of PDO at the same quality conditions of the petrochemical PDO. In the second step of the LCA, the life cycle inventory, LCI, data collection is one of the major activities. The type of data and their collection typically relates to 2 types of systems: background systems and foreground systems. Foreground systems refer to specific data needed to model a specific system, in this case the PDO production from sugar. Background systems refer to generic materials, energy, transport, and waste management systems. This data can typically be found in databases and in literature. Although it is in principle possible to investigate the environmental impacts of sugarcane production from any milling facility, for simplicity in this lecture, we will assume the sugarcane production and processing as background system. The average Brazilian sugarcane industry produces 5 main products, including sugar, ethanol, and electricity. For this analysis, we use the results reported by Seabra and colleagues. The Brazilian sugarcane industry is a multi-product system, and in that case, the distribution of environmental impacts among the final products becomes an issue. This is called allocation. ISO 14044 recommends to avoid allocation by either subdivision or system expansion, which means reducing the multi-product system to single product systems. The second option is to allocate the environmental impacts by partitioning based on physical relationships, like mass or energy allocation. The authors of the LCA study for the Brazilian sugarcane industry used the second option. They also analyzed the effects of energy and economic allocation on the LCA results. For the production process of bio-based PDO, you have designed the flow sheet and determine the corresponding mass and energy flows for each processing unit. Then, based on the mass and energy balances for all inputs and outputs, it is possible to prepare the normalized inventory tables. For example, here, 3.48 kilograms of sugar are used per kilogram of PDO produced. This value refers to the overall input of sugar, which also accounts for non-fermented sugar and for any possible losses occurring through the process. The third step is the life cycle impact assessment, LCIA, which aims to describe the impacts caused by the emissions and consumption of resources over the whole life cycle. This is achieved by aggregating the inventory results into selected categories according to the type of environmental impact they contribute to. For example, all emissions of greenhouse gases may be aggregated into one indicator for global warming, and all acidifying emissions can be aggregated into one indicator for acidification. These calculations are based on models describing the cause-effect chain for natural systems for midpoint and endpoint level of aggregation. There are several well-known methods available for midpoint, endpoint, and combined assessment. For additional information about the impact categories and methods, you can check the Hitchhiker's Guide to LCA and the ILCD Handbook. Keep in mind that selection of the impact assessment method, the impact categories, and the definition of the desired level of integration have to be consistent with the goal and scope definition and with the way you would like to discuss your results with the audience. For our case study, we focus on two midpoint impact categories: climate change and non-renewable energy use. The second aspect of the LCIA is the characterization of category indicators. This is a quantitative step where the size of the environmental impacts are calculated per category using the characterization factors. These factors can be found in databases for impact assessment methodologies or in literature. Additionally, existing data of environmental impacts for already studied processes can also be used from databases or literature. For example, in our case study, we use the greenhouse gas emissions and primary energy use values calculated by Seabra and colleagues, the tables with the LCIA results and characterization factors, and then completed for all emissions. The table on your left shows the characterization factors or emissions values taken from literature for non-renewable energy use and for greenhouse gases emissions. These factors are then multiplied to the life cycle inventory results, and then the impact assessment results are obtained. Finally, all contributions are added up, resulting in the total scores for the environmental categories of interest. Normalization, grouping, and weighting are optional steps, which aim to provide the additional understanding of the magnitude and significance of each impact category. For example, normalized results are calculated relative to a reference value or system, allowing direct comparison of alternative processes or products for specific impact categories. These steps are not commonly applied for process design due to the high level of aggregation of results. However, this type of results are preferred for communication and decision making. The last step of the LCA is the interpretation of results, which can be done from different perspectives. Consistency check, for example, refers to confirming that assumptions, methods, models, and data are consistent with the goal and scope definition. Completeness check is made to ensure that all relevant information and data needed for interpretation is available and is being used. Contribution analysis allows to identify the flows and process contribution most to the environmental impacts. For example, in this case, the steam consumption and sugar have the highest contribution to primary energy use, while sugar and electricity consumption are the major contributors to GHG emissions. Comparison analysis is useful to put into perspective the obtained results with respect to a reference system and to other reported studies. Here, for example, the GHG emissions and the primary energy use are compared to the data reported by DuPont and by other two studies, also for bio-based PDO. In these cases, the feedstocks is US corn. The same studies also report the environmental impacts for petrochemical PDO. The figure in the screen shows a blank space for the results on the GMO case study that you have been working on through this course. When comparing bio-based products and also fossil-based products, there is a fundamental difference. The carbon embedded in the bio-based product, or at least a fraction of it, is biogenic carbon. This means the carbon was captured from the atmosphere during the agricultural phase, and therefore the emissions resulting from the combustion of the bio-based product do not contribute to additional emissions to the atmosphere, unlike fossil-based products. Then, for a fair comparison, the emissions resulting from the combustion of fossil-based PDO due to waste incineration should be included. Another method to account for the biogenic carbon embodied in the bio-based product is the direct deduction from the calculated gross GHG emissions. Finally, sensitivity, uncertainty, and scenarios analysis are useful to determine the influence of assumptions, method, data, and any structural or statistical imprecision in the LCA results. For example, what would be the LCA results if different allocation methods are used for the sugarcane industry products, or if different geographical locations and feedstocks are considered, as shown in the screen, and if the analysis is performed for the time frame 2020. Those are all typical questions often addressed in the interpretation of LCA results. The take-home message today is that the LCA results are not only about the obtained results, but most important, about the data used and the assumptions made behind the results. So be very critical when looking at the environmental impacts of any system. Thanks for watching and enjoy the next unit.